Hey everyone, and welcome to this explainer for grade 9 geometry at St. Paul American School Clark. Today, we're doing something pretty amazing. We're going to build the absolute foundations of geometry from literally nothing to everything. I'm super excited to guide you through this because these core concepts, they are the exact building blocks that make every single shape, model, and mathematical proof possible. Let's get into it. Here is our roadmap for today. We'll kick things off with our lesson objective, dive right into the core terms, map those onto the coordinate plane, walk through a quick example, tackle a common misconception, and finally wrap up with a formative check and recap. Section 1, Lesson Objective, our precise goals. By the end of this explainer, you're going to establish a rock-solid foundation for identifying, drawing, and reasoning with geometry's core building blocks. You'll truly understand points, lines, and planes. Plus, we'll apply some basic geometric postulates, which are basically the universal rules we just assume to be true, and crucially, you'll know exactly how to draw and label these fundamental terms correctly. Section 2. The core terms, starting in 0 dimensions. Okay, so what's really fascinating here is that a point isn't an actual physical thing with width or depth. It's purely a place in space, just a precise location. And because it's just a location, it literally has 0 dimensions. No size, no length, no width at all. Now, when we want to show a point in our diagrams, we draw a little dot, and we always label it with a single capital letter, like point A or point P. Now, imagine we take that 0-dimensional point and stretch it out forever in 2 opposite directions. What do we get? A 1-dimensional line. A geometric line is perfectly straight. It goes on infinitely, which is why you'll see us draw arrows on both ends. And just like a point, it has absolutely 0 width. It only has length, making it entirely 1-dimensional. To name a line, you just pick any 2 points on it, let's say J and K, and call it line JK. Or you can just use a single lowercase italicized letter, like line G. All right, let's expand that single dimension. Doing that forms a plane. You can think of a plane as a huge, perfectly flat sheet of paper that just never ends. It's got length and width, which makes it 2-dimensional, and it extends forever in all directions. To properly label a plane, we pick any 3 points sitting on that flat surface, as long as they don't all sit on the exact same straight line. Or we can just use a single capital cursive letter, usually tucked up right in the corner of our drawing. This table perfectly captures our journey from 0 to 2 dimensions, along with the strict rules for how we label them. You can clearly see the buildup here, from the 0-dimensional point up to the 1-dimensional line, and finally out to the 2-dimensional plane. Getting these naming conventions locked in right now, like remembering to use a capital letter for a point, but a lowercase letter for a standalone line, is a totally essential habit for all your future geometry work. Section 3. The coordinate plane, measuring our sandbox. So instead of having points just floating randomly out in space, the coordinate plane gives us a measurable stage to pinpoint exactly where things are. It does this by taking 2 number line axes, a horizontal one and a vertical one, that cross each other perfectly at right angles. This creates a grid, a highly structured environment where geometry basically shakes hands with algebra. The real game changer here is that we can use these 2 coordinate numbers to anchor our abstract 0-dimensional points right onto a concrete grid. When you're given a pair of coordinates, those 2 numbers are handing you the precise, exact location of a geometric point relative to those intersecting axes we just set up. Section 4. Worked example, when models share space. When we analyze geometric models, we see that intersections create brand new relationships. For instance, 2 flat planes crossing each other actually form a single straight line. Think about the room you're in right now, where one wall meets another wall or where a wall meets the ceiling. That intersection is a perfect straight line. And here's some key vocabulary. If you have a set of points all sitting on the exact same line, we call those points collinear. But if you have points scattered all over the same flat wall or the same plane, we call those coplanar. Section 5, Misconception check. A common visual trap. Okay, we really need to address this because it catches people out all the time. It is absolutely crucial to remember that while the dots and lines you physically draw with a pencil take up actual space on your paper, the geometric concepts they represent have 0 width. Think about it. If you drew a dot and put it under a microscope, you'd see a big, messy blob of graphite. But in pure geometric reality, that dot is just a visual placeholder. A true mathematical point has 0 dimensions. Same thing goes for lines. Your pencil mark has thickness, but the mathematical line it represents is infinitely thin. Section 6. Formative check and recap. Test your knowledge. All right, let's put this into practice. I'm going to throw a statement your way. A point takes up space. Is that always, sometimes, or never true? Think back to our chat about physical drawings versus pure concepts. If you said never true, you nailed it. Zooming in on a mathematical point is never going to reveal any width. A point is exclusively a location on a plane. Since it isn't a physical object, it has 0 dimensions, no size, and literally takes up 0 space. Okay, here's the next one. Any 2 distinct points are collinear, always, sometimes, or never true. Imagine I just throw 2 random points out onto the coordinate plane. Can they always be connected?
That is always true. Because a line extends infinitely, any 2 dots anywhere in the universe can be perfectly connected by one single straight path. This is actually a fundamental geometric postulate, a basic rule we just accept as fact. No matter where you drop 2 distinct points, you can draw exactly one straight line through both of them, which means they're inherently collinear.
Last one for you. A line is one-dimensional. Always, sometimes, or never true. Try to picture that dimensional table we looked at earlier in the explainer. Always true. Since a line only tracks length, it represents a perfectly one-dimensional object. It stretches on forever in 2 directions to give us length, but it has absolutely no width or depth whatsoever. So let's bring it all together. Remember that we build everything in geometry from 0-dimensional points all the way up to 2-dimensional planes mapped on axes. A point, just a location. A line connects those locations in a single, infinite, straight dimension. A plane expands that into a flat, infinite, 2-dimensional surface. And the coordinate plane is our grid system, the stage we use to mathematically pinpoint exact locations using those intersecting axes. Before we go, I want to leave you with a quick spatial reasoning puzzle to ponder as you gear up for your next geometry adventure. If you have just one single 0-dimensional point sitting on a coordinate plane, how many unique 1-dimensional lines could you draw straight through it? Close your eyes and try to picture it. Thanks for joining this explainer, and keep thinking geometrically.